Well, now another use of mass spectrometry is the selective reaction monitoring. Right? This is also called tandem mass spectrometry or mass spectrometry, or simply MSMS. Okay, here, this one is from the chromatography. Okay, and ions enters these 1 to 3 quadruple mass spectrometer, right? So you use 1 to 3, Q1 and Q2 and Q3 mass spectrometer. Okay? But let's examine what each the quadruple mass spectrometer, what are they doing, right? This one, the first the quadruple mass spectrometer, you only select only among these many ions of different masses, and then you select only one, yeah? One ion passes, right? And then in in Q2, okay, in another quadruple mass spectrometer, then there is a inside the this mass spectrometer, there is a fragmentation occurs, right? Because inside this Q2, your ions now collide with these gases, nitrogen or argon gases, and then fragmentation occurs here. Okay, and this fragmented ions, which is called product ions or daughter ions, right, enters the Q3 quadruple mass spectrometer. Then it is detected. Okay, here. So only selected ions are detected by the detector. Okay, this is cutaway view of tandem mass spectrometry. Okay, here the samples enters the first this quadruple mass. Actually, this is kind of a mass filter. Okay, quadruple mass filter. And then Q2 is collision takes place in Q2, and in Q3 you select only you know, the selected ions of your interest. Okay, yeah. And then let's see how the technique is applied to detect estrogen, right, from the I think liver. Yeah. Let's look at this first figure here, and then electrospray tandem mass spectrum of pure estrogen, EE2, full spectrum of fragments. Yeah. So at Q3 stage, yeah, you detect the fragmented, the species. Okay. Now it shows only the fragment whose mass to charge ratio is greater than 140 here, right? From 145, yeah, 159, or like that. Okay. Mm. And they are measured by Q3, and this figure B is a subsequent selected reaction monitoring. Only the product ions at the mass to charge ratio is 159 and 145 would be selected by Q3. Yeah, among yeah, there's many peaks. You only selected yeah, these two peaks. Yeah, this one shows not this one EE2. This is the what? Mm? This is the the estrogen, right? Estrogen EE2. Yeah, this is your real peak. Yeah? But the x-axis is time. Now this is connected. This QQQ, tandem mass spectrometer is connected to liquid chromatograph. Okay, and in this figure you see there is a very big peak at this time, right? But this is now definitely E2. Okay, but very accidentally the same you see, same mass signal for mass to charge, which is 159 plus 145. This one is detected. You don't. It is not known. It is not certain. Which species contribute to this big peak anyway. There are other compounds that contribute to match spectral signals for this same set of masses. Okay, yeah. This one, this is original peak. Yeah, the molecular peak minus this one hydrogen, and this is fragmented into these two peaks. But actually, what we wanted to detect signal at this the time, but the short time there is a very big peak. Okay, but in this elution time of 15 to 18 minutes. Okay, at the moment, this is not known. Well, anyway, this tandem mass spectrometry, right, is a very, very powerful technique for detecting very extremely low concentration, small amount of samples. Okay, next topic is the spray of proteins. This is well suited for the study of charged macromolecules such as proteins. Okay, when proteins undergo electrospray, it takes not only a single charge but also many charges. Okay, many charges. Okay, this is a typical example of electrospray mass spectrum of proteins. Actually, which protein? Let's see. Transferrin. Okay, protein transferrin. As you see, the proteins, the molecular mass is very big. Very big. So, this electrospray method is a good technique for studying the proteins. Other technique is MALDI-TOF. Okay? You'll see soon. Where after electrospray of proteins, usually you find there are many peaks, many nicely looking peaks. Okay, and then each peaks are not equally separated. Okay, but there must be a pattern from this spectrum. Now we can very rather easily calculate the protein's molecular weight. So our question is how do we know the charge and molecular weight from these peaks? There are many peaks, 1, 2, 3, 4, 5, 6, 7, many peaks. Okay, and let's look at that. For example, this peak, its mass to charge ratio is 2652.7, right? And its charge is 30 plus 30, okay, very high. And this one is charge is 36 plus 36, and this is plus 40, right? This is multiply charged species. Okay, let's find the charge and molecular weight from that spectrum. Okay, for a peak with mass to charge ratio is m n. Okay, here is n is number of protons. Okay, for when there are n protons in the in molecule, right? And then what? This one. Mn is now is m mass to charge ratio is Mn. This is mass divided by charge. Since it contains n numbers of protons, you have to divide by n. Okay, and also the mass you have to add the proton mass, yeah, and multiplied by n. Okay, this is mn peak here, right? Then this gives us the large m over n plus 1.008. This mass is the proton mass. Okay, and you see, if you subtract this number out, then you get this one. Okay, and what about the other peak? When a proton, one more proton is there, and we do the same calculation here. Okay, the total charge is n plus 1. Yeah, and the molecular the mass is molecular weight plus n plus 1 multiplied by 1.008, and then we get this one, this formula. Okay, and we divide these two equations. Okay, and then we get this very simple equation. Okay, and then rearranging this equation, we get the number of protons, and E equals this one. Okay, very simple. And molecular weight is what? Molecular weight, very simple. Yeah? Molecular weight n multiplied by this one, n m sub n minus 1.008 here. Okay, because here molecular weight from here, m large M is given by the n multiplied by this part. Okay, let's apply that formula to this table to get molecular mass. All right, here let's take these two peaks, okay, as an example, or you can take any two peaks here. Okay, any two peaks. Okay, let's take these two peaks. All right, but now you don't know how many protons are there. Okay? Simply we apply this formula, right? This n is number of protons. Okay, let's take this one, this peak as a reference. Okay, and n equals m this let me see, this mass number minus 1.008, and this mass number minus this mass number. Okay, and then by substituting all these values here, and then we get 30.013. Yeah, oh, this is almost 30. So we know this peak. Yeah? This peak contains 30 protons and one, this molecule. Okay, and what is the molecular weight? Yeah? 30 multiplied by mn, this one, this mass number, minus 1.008, and then we get this big number, 79,551.44. Right? This way you can calculate the molecular weight. But pick any two peaks, and then you do the same calculation, and you must have the same molecular weight. Right? Otherwise, that doesn't make any sense. Yeah, this table shows those calculations. Okay. Yeah. Observe the mass here. Okay, these masses, and when you take the difference, yeah, and then you get this one for each one. Yeah, and then the difference between this one and this one, yeah, between the two peaks, right? And then you get these values, and then charge number, and using this formula, you calculate the number of protons for each peak. And then you get, although you take any peak, yeah, the first one, this one, and then you get the 30. And if you take, let me see, let's see, this one and this one, and then you get 31, right? Okay. This one is number of 31 protons in the structure. Okay, and for this one, the next one, and then you do the same calculation, and you get the number of protons is 32, like that, right? And using this formula, and then you get molecular weight here. But molecular weights are almost same, yeah, within the experimental error. Yeah? So mean value is what? 79,551.78, right? Wow. This means that, no matter what peaks you take, you get almost identical molecular mass, right? So this is a very powerful technique. Electrospray of protein is a very powerful technique to get the protein's molecular weight. Okay.